Good morning, everybody. I'm Peter Brusilovsky. I'm the second author. The first author is Shahaya Sherry Sahibi. Is a senior PhD student right now. Unfortunately, she should present that paper. I think she did a great work. She wasn't able to come because she's Iranian, and Iranian has a real trouble to travel outside of the United States. So I'll try to do my best presenting the paper. The paper is not very typical for our group. Our group mostly works not on algorithms but on adaptive intelligent interfaces. But there is a reason for that paper. I will explain how we kind of get into that mess. So first of all, just in case you don't know what is cross-domain recommendation, collaborative filtering specifically, the idea is very simple, and there is even a book of that. If you like Devil Wears the Prada book, will you like Devil Wears Prada movie? So if now you taste in movies, and you have a lot of ratings on movies, if we start new recommender system on books, can we use all of that information to help you to find a good book? And in fact, the majority of early papers, they did focus on books and movies. And most of the idea of the papers to show, yeah, it helps. So that's actually partially our idea as well. Would like to figure out to what extent using external additional domain can be helpful in boosting the quality of recommendation in the target domain. We call them auxiliary and target domain. But there is more to that, because it's been already almost 10 years since the early work on cross-domain recommendation appears. I'm glad to see here Zvika and Shlomo, who wrote one of the first papers on the topic, which was kind of inspiring for us. But it's not the matter to tell, okay, yes, it helps. But it turns out the situation is not that easy. Sometimes it helps, sometimes apparently it's not. I'm not sure whether Braha Shapir here, I've seen her yesterday. She published a very interesting paper which shows that in some pairs it really works well, and some not. What is the magic? Why one domain may help to another, but another is not going to help? How to figuring out which domain is good? So it's our second goal, how we can distinguish this good and bad pair and uncover the magic. Maybe we can recommend specific domains. If you would like to get better recommendation books, get, for example, recommendation, I don't know, games. What you game for is what you need to read. Well, so we get to that point through actually a sequence of different things. Our original goal was to boost quality of recommendation in a specific talk recommendation system using everything, because when you recommend talks, you're starting empty. And we used all kind of external data to do that. There's a paper about that. And then we came to a very nice idea. One specific kind of external data might be recommendations and ratings from a different domain, which we potentially could use. And then through a sequence of trials, we really found that, well, different domains not working together. So we're trying to figure out how. And we get the key idea. So we found canonical correlation, which I'll tell about what is. And we think, oh, canonical correlation is the right thing. It may be a potential way to figure out which domain pairs are good, which are not. And then we get an idea, well, as long as it's such a good idea, can we get a whole recommender system approach based on canonical correlation, which seems to be quite innovative. And these are, I will publish my slide on SlideShare, and these are basically 3 papers which represent the 3 different stages of our work. But let's focus now on the last part, the current paper. So what we're trying to do here is essentially 3 things. First of all, I would like to explain the whole idea of canonical correlation and its use for cross-domain needs, including testing two domains, whether they're good or not for each other, and also as a way potentially to use canonical correlation as a recommender approach. And then we're trying to figure out, using several different parameters, including canonical correlation, which domain pairs are good for each other, which are not, which can tango and which are not. And we really try a range of different things in that, and I'll walk you through all of the parts of the process. So first, to introduce that kind of new thing, what is canonical correlation analysis? That's a very complex and one of the most fancy multivariate statistical model. So we're trying to maximize correlation between 2 data set, multiple dimensions. So we're trying basically to find how to turn the data set in one domain and in another domain, so they kind of look alike, more or less correlated. It's very hard to explain in figures, so Sherry get very nice pictures. And I'll try to explain it kind of in a term of the domain. So let's say we get two items, well, two specific movies, let's say Avatar and Titanic, same director. And we can get user ratings on the two different things, and you can see they, to some extent, correlate, to some extent don't, right? So as in the leftmost figure. And then we do another domain, say books, and we get something like, for example, Capital, Karl Marx, and, well, it's probably not a really good example, but Mysterious Island in Harry Potter. And they kind of also maybe correlate, but not really very good. Now, it might be that we just need to represent the importance of different book and different domain and scale them properly. So if we get, for example, 0.2, this is the bottom picture, 0.2 of Harry Potter and 0.8 of Mysterious Island, and then we get the same combination of that two movies, Avatar, then mysteriously, the users will get a very correlated test. They either don't like that interesting combination or like it altogether. So that's kind of idea based on the fingers. If you'd like to put it mathematically, this is essentially approach to maximize the correlation between two matrices. So matrix X by n, matrix Y by n, and it's the same number of users. And the number of items, the domains might be different, so we need to transpose them so that we can multiply them. And finding a set of coefficients, W X and WY, which is essentially a way to turn the dimensions in one domain in another domain, so that after all of that, the correlation will be maximum. And this is the proper definition of the problem, but if we can see that we can actually cut out of this equation, this coefficients from the top and the bottom, because it's just proper scaling, and we define it much easier, a way to maximize that product, given that we normalize the weights within the domain. So that's kind of mathematically, if you had more question about that, you better ask Sherry. I can provide you email address. We fight with that for quite a while. Now, what is the point and how we can now reconsider or re-explain that in the term of cross-domain recombinator? That in fact, that's exactly what I've showed you here. So one dimension or one data set is the items in the target domain, another data set is items in the source domain. And what we need to find out that subset of items in one domain, subset of items in another domain, and their linear combinations, which in fact perfectly or more or less reasonably correlate between users, and we have the same users across two different domains, kind of like that, right? And of course, this is a reasonable correlation, might not be perfect, but we would like to try to maximize that. And then after we maximize, then we still see is it large or small. Well, it's just maximization, potential coordination between domains. The idea of that is the best way to align two domains together. And if we would like to use one domain to help to another domain, we probably need to learn as much as possible from the kind of the big picture, so we can maximize the chance to use information from one domain for another domain. This is the way, well, basically to apply it in cross-domain recommendation. One idea is basically calculate that. So let's try to maximize that correlation and find out what is really that correlation. Is it high or low when it's maximized? If it's high, maybe the domains are really similar to each other because we've managed to align them reasonably properly, at least with some subset of items. And if it's not, whatever we're turning, well, so there's no luck, domain is not really good. So this is the first idea. The second idea is more complicated because the idea is the following. As long as we try to look at the big picture, we look at the data from two different domains, we align them, we find the coefficients, we find the raw correlation. Okay, then in fact, we have everything in that equation to take out one of that parameters. If we learn everything from two domains, right, now we can basically predict the data from one single user from one domain, and we have data for that user in another domain. So kind of take X out of the equation, put it on the left, and that in the simple form, it looks simple, and this form it looks like this. So in fact, we can really resolve it, assuming that the user ratings in the target domain are completely unknown, or partially at least unknown. We can, because we learned the general coefficients, all that part, right? We learned the pattern of communication. We can really predict user ratings from the target domain. Okay, now does it work and how it works? So we, as I say, we're going to analyze 158 domain pairs and ask several different questions in a row. So where we get so many pairs, and actually this is the major trouble with cross-domain recommendation. We try several different things, but to get an extensive investigation, we need to find the system and the data set which allows to examine so many pairs. So in that case, we take Yelp academic data set, which is not ideal, and I'll discuss it at the end. If I will not have time, ask me a question. But it's at least a reasonable domain, has a lot of specific subcategories, which we actually group together so that we get a reasonable amount of data. We ended up with 21 categories after grouping. Within that categories, if you know Yelp, the ratings of the things within the domain are between 1 and 5. And what we want to figure out with this excellent data set, to what extent the success of cross-domain recommendation really depends on the pair, because different pair may work or may not work, and now we have a lot of pairs. But the second question also, is it just the pair? Is it really taking two domains which are kind of similar and then every approach will work? Or in fact, getting good approach is also very important. And so that's the second kind of question, and we get here two cross-domain approach for recommendation and one single domain approach, which is kind of classic one. So this is a data set characteristics. As you can see, domains are very different. In some domains we have almost no users. Some domains have a lot of users. And so that's one of the trouble with this data, and sometimes rating density is reasonable, sometimes really completely miserable. But that's what we get. And we actually like to continue that work. And before I move any further, if you are in a company and have great set of cross-domain data, like, I don't know, Amazon.com or something like that, we would be very happy to try that again in a better domain, because Yelp is good because it's available, but it's not perfect. Okay, so now how we can figuring out which pairs. So for first of all, we need to make sure that we get a reasonable amount of common users between two domains, because generally there are common users, but maybe not necessarily between two pairs. And also we would like to make sure that the number of common users, number of items is larger than the number of common users. Otherwise, we probably don't really complete noise. So we get 158 domain pairs, and then for every pair we run the experiment twice, using A to predict B and using B to predict A. So the second part is the approach. As I presented, our target approach was a cross-domain CCA, which we hope can do more by learning the patterns of domain correlation and maximizing the amount of information we can extract. But maybe it's not really the pattern, it's just the data, right? So we tried kind of classic settings, cross-domain SVD, where we concatenate two matrices. And also as a baseline, we use a single domain SVD, which is not taking account any extra information, extra domain. So this is the setup. So for one domain, this is classic SVD setup, basically. So training, testing, 80% data used to predict user, and then 20% to test whether we really can recommend something for the user. And we can do it with a single domain, or when it's cross-domain SVD, we just join the matrices like you have it here. So for CCA, it's a little bit more complicated. So we need to get 5-fold user-certified cross-validation. So we get 80% of items for training, 20 for testing, and we also get some kind of seed up from the target user, so we can kind of learn something about that. And we would like to predict the majority of missing ratings. We're also using 15% of the items and testing data set to learn the parameters. So again, well, I can tell you more about details, but I'd like to focus on the main part. Now the results, as you can see, show two trends. Trend number one, and this is actually RMSE, trend number one, it really depends on the pair. Sometimes on the pair RMSE is high, sometimes is low, but more or less as a kind of continuum. And the other kind of thing, you can see that the red is kind of under green, and red is CCA. They're kind of looking like CCA works better. But of course, we need to try it more formally. And more formally, maybe we should look at that first. More formally, we found out that cross-domain, in fact, CCA does work much better. So CCA works better than SVD in cross-domain settings in 74 domain pairs, and works better than single domain in 77 domain pairs, and it's significantly better. And in fact, cross-domain really helps, because SVD on cross-domain works better than SVD on single domain, but the difference is not that large. We only can find significant difference on 9 domain pairs. And for the rest domain pairs, the reverse is never true. So it's never the other equation. It's either non-significant or it's significantly better. So essentially we have two messages. It does help to have external data in general, at least not harm. And CCA really works much better in extracting the patterns of similarity. And in fact, what we can see also, it really depends on the domain, because if we can, so we have so many different pairs, we actually can correlate the performance of different algorithms. And you can see that cross-domain correlation and single-domain correlation for SVD are very highly correlated. The correlation is 95%. So essentially, if the domain is bad for recommendation, it's bad for cross-domain recommendation. But the correlation with CCA is also high significantly, but not as good. So apparently, when we get something else with different data and using it in a different way, so the result of cross-domain SVD and cross-domain CCA are not exactly correlated. All right, so now what are the characteristics? Which domains looks good and which are not? Now, because for every domain we have a lot of parameters. We know how many users, what is the ratio of users to items, what is the density, number of common users. We can try a bunch of different things and see how they correlate with success. But first of all, we need to define the success. So what we would like to do is to switch from the error itself to the improvement. And improvement is how much we can decrease the error comparable with the baseline. So this is a different formula. This is how much the cross-domain approach really improves the error. That's what our definition of what works. If it can significantly improve the quality or decrease the error, that is the case it works. Okay, now what does it mean it works and which domain features are really correlating with works? Surprisingly, and we try a bunch of different things, almost everything we tried positively correlates with improvement. So the more users we get in target domain, the better. The more users we have in source domain, the better. And in particularly, what we wanted to find out, the larger is the correlation coefficients, and then that means the more domain are correlated, and we try 3 different settings. The percentage of correlations in above 0.8, above 0.9, and above 0.95, increasing demands. The more, the better it works. So yes, indeed, canonical correlation shows something really interesting. The better is that correlation between the domains, the higher is the improvement. The higher correlation is with improvement. And by the way, this is the way we calculated the improvement ratio. We try RMSE for one domain and for another domain, normalize that. So it's relative. So almost everything is again significant, so kind of really nice. But what is really most critical, and I'll jump a little bit further, a little bit ahead. Where is that? Right. So what is not really significant is that the target user size to target item ratio, which we thought should be a really good predictor, but in fact it was not. All right, now we would like to look at the nature of the suitable domain pairs, and we try to get a number of additional parameters and try to figure out what makes domain pair good. And we try to do it in 2 different directions, because what we want on one side, what we have is real performance. We know for which pairs improvement from cross-domain approach is large. Right, that's apparently is what makes the domain good for a cross-domain. If we edit data from another domain, an improvement was large and significant, yes, that's a good pair. They can tango, but we can also try on the reverse direction. So the question in one direction, if they tango, is the correlation high? And we already see that there is a very good dependency between high correlation and improvement, but is it really direct dependency? But on another approach, if the correlation is high, do they really good to work together? Is it the same thing, high correlation and the high level of improvement? In addition, we kind of looked at meaningfulness, right? So if you get something unusual, and in our earlier approaches, when we get a wrong formula, we get some magical results, then we allocated user taste in perfumes with the books they read. And we kind of already imagine New York Times, what you smell is what you should read, right? No, it turns out an error. So we have to be really careful about that. So we look at the meaningfulness as well. And we kind of, that is the case where we didn't really get quite really good results. So And we look at the case with high percent correlation to define which domains are good. And in many cases, we really get what we wanted. So there is a large correlation. The domains look meaningful. For example, food and arts and entertainment. And indeed, there was significant improvement. So it seems to be the proof. Indeed, improvement, semantic similarity, and high correlation is kind of the right thing. Unfortunately, we found a bunch of cases where it's not really working just like that. So, for example, we can domains where they kind of close to each other. So, for example, restaurant and nightlife, they should be close, right? Restaurants, people go in the night. Unfortunately, it looks like SVD is not getting that, right? So, vice versa, we have domain pairs with high correlation, but they kind of very strange cases, like shopping, arts and entertainment, and pets and nightlife. I don't know, maybe people are walking pets in the night, so they have correlated tastes. In other cases, we also get things where the improvement ratio is high, but correlation is low, or vice versa, cases where correlation is high, but improvement ratio is no. So if you look at the picture in general, we see that the high canonical correlation apparently helps. But if you like to look at one-to-one dependency, it's not kind of really good. So our first simpler question in fact turns out to be not negative, but, well, not exactly right. And the second, more complicated, can we really use it for recommendation, turns out to be a success. So we really like to continue that work, and I think one of the troubles that we have with this domain, first of all, the sometimes low number of ratings in some domains, which we still want to use because there are we need a lot of pairs to find correlation. But another thing, I really don't think that the ratings in Yelp is the same as the ratings in Amazon, let's say in Netflix. Because you might, for example, you don't like some food in the restaurant, and you don't like, but you don't really rate the restaurant. And as a result, in the Yelp data, we might get a lot of noise. And as a result, when we get CCA in that noise, we're not getting anything together. So maybe if we try it in a better set of domain pairs, where user recommendation is a reliable representation of items, rather than kind of random. So, like user rating the restaurant, right? Not the specific one experience. Maybe we can get better results. So we still want to try, and we welcome everyone to collaborate. So now, just a quick summary of what we wanted to do and what we did. So we get this interesting idea that canonical correlation might be the new tool, the new gun in the cross-domain correlation, cross-domain recommendation area, which might change the game because we knew it sometimes helps, sometimes not, and we thought that canonical correlation may tell us when it's a good idea to use two pairs and where not. And then the second idea was, well, as long as we can use it to predict, we in fact can use it to recommend. And to figuring out to what extent canonical correlation and other factors can help in finding two similar domain pairs which can be helpful to each other. We get a large set of domain pairs, examine them, and try to find correlation between improvement, different factors of the domain, such as user-to-item ratio, density, and, in fact, canonical correlation coefficients, and the way to what extent using data from another domain can improve the situation. We also try to do two different algorithms at the same time, so we cannot say that it's not really cross-domain, but it's the algorithm. Because we now have two different algorithms which use cross-domain information, we can really argue that if there are improvement on both sides, it's really external data, not just a specific fancy algorithm. And that is this specific set of conclusions. And, well, I think that's it. I said something between 20 and 25 minutes. It's been 22. So I guess time to answer questions. All right.
So, yes, thank you very much. We have time for a few questions. Or do we have the microphones? Ooh.
Green. I have this one.
So I'm a little bit confused now. I think that you could the correlation analysis basically kind of rotates the latent factor decomposition, and you also require that there are users that are in both domains.
Yes, that's
And,
important thing.
I think you can do the same by just, let's say that is book and movie. These are the two domains. You can just take the book and movie ratings for users and then apply the standard matrix factorization technique. And you don't even require that there is a user that rated a book and a movie. And you get this joint latent factor, the composition for both book and movie domains. So you had also experimental setup, and I didn't get it whether you even compare with this kind of setup where you do a joint to take the examples from both domains and then use matrix factorization to discover the latent factors for both domains at the same time. So I guess my question is whether you need your technique basically.
Well, I think that, of course, this is the idea that we try to find latent information, but I think it does matter to how we can find it, because the original idea, lots of early work, is trying to use that, right? They really just concatenate two domains, let's just get books and movies together, and let's try to extract latent factors. That's actually what SVD is doing. That's what we did as a baseline. But it turns out that SVD, at least in that case, is not good enough to extract latent factors from not processed domains, not prepared domains. We have raw data, and it turns out that we can use another statistical approach before we try to apply that, right? Which in fact try to maximize our chance to learn from one domain for another. And that's the magic of canonical correlation. Don't throw away raw data, right? Which try to extract classic latent factors through factorization or whatever else. But first try to prepare the domain, try to align in a way so that you maximize your chance to extract that. So they're kind of two different parts to work. And we can try some other combination, but I think that kind of preparation, that's a very big deal here.
So the zeros in the lower left-hand side and upper right-hand side corners for the item user rating matrix confuse SVD, basically. Is it the kind of intuition?
Exactly, because the items, SVD is not doing magic, right? And it's not even has been designed for using that approach. And the question is, we can do better. And the idea was that SVD really, the canonical correlation really can help. And that might be actually more universal. In that case, we applied to improve the data in one specific case. And maybe in the same way apply it in different cases. So will it really working? We're not completely successful. And I think noise has to deal with both failure or SVD and failure or not really perfect performance CCA. Oh, Shlomo, right.
Yeah.
The founders.
Yeah, the founders. Yeah, good. You use CCA, and it worked. It helped the accuracy. Just sort of thinking aloud, have you considered causality? Causality rather than correlation.
Oh, I don't know.
We know the difference between causality and correlation. So, something may be correlated, but...
That's a good point. It's a kind of philosophical approach. Yeah. Generally, we can really think about it philosophical, but in other ways, we actually can look at the temporary basis of what really counts user. It's maybe that watching some movies, in fact, change user in a way that the ratings of books can be changed. I don't know. In that case, as almost all other recommender system approaches, we just ignore causality and temporal dimension.
Or actually, it's not only temporal. It can be that there are 3 domains, and actually you're looking at 2, but the origin is coming from the same
very good question. Actually, Sherry is now trying to consider temporal dimension in different settings in educational recommender systems and applying 3-dimensional or tensor factorization. But we never brought that two ideas together. Thanks to this thing, we probably can bring it together in the work. Yeah, still have 1 minute.
So I'm not sure I missed that, but did you mention that the sizes of the data sets you have? So if you split the data, it's not. So what's the size, the number of ratings you have? It's not here, is it? Min-max density.
There are data about that in the user numbers and then item numbers, user to item. So we have all of this data.
Yeah, I was wondering
if... Not really here, right? It's just to characterize domains to show how different they are. And also, what is also very critical, that the number of similar common user into pairs very different.
Yeah,
right?
my question is, when the sizes of the small data sets are small, so maybe you're into a very strong cold start situation so that you only have the effects of cross-domain collaborative filtering because of the cold start situation.
Yes, I think this is the case, but the main idea of using cross-domain recommendation is to help in the cold start situation. And we don't have any evidence that when we have a lot of data, it's a great help. So most of the time it works in the case when the number of ratings is small, which is generally the case in the whole Yelp data set. So that might be the reason why it works so really well for Yelp. If we get too densely overlapped data set, maybe we will not be able to reach this level of improvement. I don't know. But I do think the results to some very large factor are affected by the kind of data set we have. So that's exactly why we want to work with other data sets. Right, thank you very much.
Yeah,
I can answer more questions in the break and then or ask Sherry if you have specific tough questions. Right, thank you.
Okay, thanks again.
Good morning, I am Filippo Bistaffa and I'm here to present my work entitled Recommending Fair Payments for Large-Scale Social Area Sharing. So this is a joint work between the University of Verona, the Technical University of Crete and the University of Southampton. So social area sharing is the problem of arranging shared rides or cars among a set of agents which is connected through a social network. So in particular, the objective here is to recommend the optimal car arrangement, the one that minimizes the total travel cost, and also to recommend the individual cost for the passenger of the cars. So ride sharing in particular is a very trendy topic at the moment, and there are a lot of companies working on this topic like Uber and Lyft. So in this work we model the social ride sharing as a collision formation problem, which is a well-known technique in the field of artificial intelligence. And so to better understand how we model this problem, let's look at this example. So here we have 6 agents, and we can see that, for example, these 2 agents can go together in the same car. So what we do is we propose to form a shared car between these 2 agents, and we also propose the optimal path for that particular car. And we do the same for all the agents. So you can see here that basically collision formation is a partitioning problem. And here in this example we have 3 partitions, and the set of these 3 partitions is called a collision structure. So to minimize the travel cost, we have to assign a value for each car, and we decided to assign the transportation cost for that car as a value for each collision. So in order to consider also the social aspect of social resharing, we enforce constraints on the formation of collisions. And in particular, we consider a collision as feasible. So it can be a part of the final solution only if it induces a connected subgraph of the social network. So here you can see that this particular collision is feasible. Because basically these 3 agents know each other either directly or not directly. But if we take the red guy away, the resulting collision is not feasible because there is no social connection between these 2 agents. So formally, the collision structure. Formally, this problem is called collision structure generation, and basically, it is the problem of finding the optimal partition of the set of agents. So here, this particular collision structure is optimal if the sum of the cost of these 2 collisions is the minimum over all the possible partitions. And you can see here that this is a hard problem to solve because, in general, the number of possible partitions is exponential in the number of agents. So To solve this problem, we use an algorithm called CFSS that we proposed in the last year. And if you want to find more details about this algorithm, you can find them in these 2 papers. So in this particular work, we are interested in the following part of this problem, which is called payment computation problem. That is the problem of recommending the individual cost that the agent should pay in return for the shared ride. So, for example, assume that these 3 agents go in the same car. They have to pay 10 euros for as a total travel cost. They have to decide how to split the bill among the 3 agents. So, formally, this problem requires to compute a vector, which is called a payments vector. And of course, you can find a lot of ways to compute this vector. So here we focus on computing stable payments. And we do this because, in general, stability is a fundamental requirement in scenarios in which agents are self-interest. Because if you don't provide stable payments, the agents may deviate from the computed solution because they may have a better alternative from their individual point of view. So stability is a very well-known concept in game theory, and it has been defined in a lot of different ways. So we have a lot of stability concepts, like the core, which is a very strong concept. But unfortunately, the core cannot be computed for large-scale instances because it's very hard to find core stable payments. So in this work, we adopted the kernel as a stability concept, which has the advantage that it is feasible and practical to compute kernel stable payments for large instances. And also, it is guaranteed that a kernel stable payment allocation always exists in contrast with the core. So the kernel is defined as follows. So a payment allocation is kernel stable when the surpluses of the agents are balanced. So what is a surplus of an agent with respect to another agent? So here you can see that the surplus of the agent I with respect to the agent J is defined as the maximum over all the coalitions that include the agent I but do not include the agent J of this quantity called the excess. And this quantity quantifies basically how happy the agent I how happy the members of the coalition C are with the current payment allocation. Because if the first quantity is way higher than the second one, basically they could have a better cost if they form the coalition C. So in the definition of the kernel, when this surplus is high, it is intended as a potential, as a possibility of the agent I to threat agent J, because he can say, look, I have this coalition here, C, that we can form without you. So he may threaten the other agent to leave the current coalition. So when this doesn't happen, the definition of the kernel consider the payments stable, and this stability can be seen as a measure of fairness in the cost distribution, because when this form of threat mechanism doesn't happen, we can consider the agents happy with the payments we provide. So how we do compute kernel stable payments? So this is done by using an iterative algorithm that converges to a kernel stable payment allocation. And each iteration we do the following. We start with a surplus matrix which is not balanced. we compute basically the two agents which have the maximum difference between their subclasses. So here are the cyan and the yellow agents. We compute the difference, and we evenly split that difference between the two agents. So here we lower the payment for the cyan agent because it is the one that has more power, considering the surplus definition. And then we increase the payment for the yellow agent. And as a result, we obtain a surplus matrix, and thus the payments are kernel stable. So in this work, we have proposed the PRF, which is an algorithm that computes kernel stable payments in the context of social ride sharing, and that is able to scale to large-scale instances with thousands of agents. And this is a significant improvement with respect to the state of the art, because previous approaches were purely theoretical algorithms that couldn't scale to realistic instances. And furthermore, we propose an efficient parallelized version, which is up to 50 times faster than the serial version of PRF. And finally, we validate our approach on realistic data. So in particular, we consider a realistic dataset for both spatial and social data. So in the first case, we used the GeoLive dataset to get the starting and destination points of the agents, which is a dataset provided by Microsoft Research. And for the social connection, we used a graph sample from a large crawl of Twitter done in 2010. So in our first experiment, we looked at the performance of our algorithm, and in particular, we measured the runtime while solving large-scale instances. And we differentiated between three different scenarios in which we varied the patch percentage of the drivers or the agent that own a car in the system. And you can see that basically the low and high density cases are easier to solve, and this is because we have additional constraints that reduce the dimension of the solution space. And even in the hardest scenario, our approach is able to compute a kernel stable payment allocation for 2,000 agents in less than an hour. And this is a significant improvement with respect to the state of the art, which is and the algorithm by Sherry and Krauss. So here you can see that the previous approach could not be used in realistic scenarios because it is over 2 orders of magnitude slower than our approach. And finally, we studied the values of the payments, and we found an interesting correlation between the ability of an agent to achieve a good payment. So in this plot, you can see on the x-axis the normalized degree, which is the degree normalized between the minimum and the maximum value, and the same on the y-axis, in which you can find the normalized cost. So we normalized these parameters because by doing so we could compare the results from different instances. And so you can see that basically if an agent has a higher connectivity in the social graph, it will achieve in general a lower cost, so a better payment. And this is reasonable because if an agent has a lot of neighbors, it has a lot of alternatives, a lot of possibilities, and so it has more collision it can form. So so if you consider the definition of the surplus, it has more possibility to thread other agents and achieve a better payment. And also, we measure the difference between drivers and riders. So riders are agents that do not own a car. And in general, drivers pay 16% less riders. And this is reasonable because riders have less possibilities to form collision because they cannot form a collision on their own. They need a driver to form a car. And also, this is a desired property for our system because we want to incentivize drivers because they are fundamental in the system and they have to provide the car, they have to do the tour in order to make the ride sharing possible. So this is a positive aspect of our approach. So to conclude, in this work we proposed PRF, which is the first approach that can compute stable payments in the context of ride sharing, and we're able to do this for thousands of agents, which is a significant improvement with respect to the state of the art. And also this is possible because we propose an efficient parallelized version. And finally, we have found an interesting correlation between the ability of an agent to have a low payment should be, and its degree in the social graph. So in the future, we would like to improve the scalability of our approach even more by studying different parallelization techniques. And in particular, we would like to implement this approach on GPU, which are general purpose graphics processing units. And also we would like to study how the use of approximate solution in the collision structure generation problem affects the quality of the payments of the agents. So, thank you.
Time for some questions? No.
Do you have any information about the robustness of these allocations or recommendations to change? I mean, the idea that we know everyone's travel needs, have an hour to compute, and everyone's going to follow this seems fairly unrealistic. You know, certainly in the Uber world and the Lyft world that you alluded to, you know, we need to make dynamic changes on a period of seconds or minutes. But even the casual carpooling examples that exist are people who change their mind in relatively short order. And is there any property in the algorithm that you have that talks about if a change needs to be made, if a particular assignment needs to be broken, whether you can repair it locally with bounded cost, or whether the entire thing falls apart when anything breaks?
So you're talking about like some sort of dynamic ride sharing. So yeah, this is a static model, so we do every calculation offline, but we are looking at dynamic ride sharing. Unfortunately, it is a very hard problem if you want to guarantee some sort of theoretical guarantees. And we are looking at probabilistic models to model this kind of behavior, maybe knowing that, for example, you can have some requests from certain parts of the city, so you can have the distribution of the request over time. You can exploit this to have like a probabilistic model to predict those requests.
Yeah, just a quick question about optimality. So it seems like you're going for an optimal price as opposed to a fair price. So is it actually that important to get the best optimal price overall, as opposed to having a fair price as a user, that they're not surprised by the price?
I'm sorry, I didn't get the question.
So what I mean is that from the point of view of a particular user sharing a car, they might not care if they're being overcharged compared to someone else in the city. All they care about is that they have a fair ride share with the person that they're sharing with.
So what do you mean by fair in this case?
Well, so if you have a rough idea of how much it costs for petrol, then as long as the person's not charging you obviously more than some approximation of how much it costs to get from point A to point B, then you probably won't question it.
So maybe the question is, your assumption is that all your participants in your market are behaving rational, right? So what is that, if that is not true? So if people just pay more or others accept whatever price, or some others say, this is not enough for me, I want more, what happens then to your model?
Of course, we work under the assumption that everything is rational. So I don't really know what happens if you drop this assumption, because we wanted to provide some quality guarantees and some stability guarantees on this payment system.
Okay. Other questions? Maybe one quick one. So in your approach, you limit yourself that you have only coalitions of people who know each other or friends of a friend. Why?
Oh, because this is a standard definition in the AI literature. So all the work that consider graph constrained coalition formation have this particular definition. But you can easily incorporate other kinds of definition. So the CFS algorithm you see there so for example, you can have another definition of feasible coalition, and you can easily incorporate that in the.
Yes, but from the application perspective, is there any requirement that people know each other to share a right, or would you run into complexity issues if you allow any possible coalition in the network?
Well, yeah. If you allow any possible coalition, you basically have basically this problem is way harder to solve. So because you have to solve this problem first in order to compute payments. So if you have all the possible coalitions, this problem becomes way harder. So you have to solve this one before computing the payments.
Okay, then thanks again.
Welcome everyone. My name is Amjad Al-Mahari. I'm going to talk today about learning distributed representations from reviews for collaborative filtering. This is joint work with Kyle Kastner, Kyung-Yoon Cho, and Aaron Corville at the University of Montreal. So first I'm going to give a quick review about matrix factorization for collaborative filtering, and specifically the problem of overfitting. And then I'm going to talk about using reviews as extra information, and present a framework for rigorizing matrix factorization using reviews. And specifically, I'm going to present two neural network-based models for reviews. The first one is distributed bag of words, and the second one is a recurrent neural network. And finally, talk about some experiments. So the core problem of recommendation can be specified as given user U from a set of n users and an item I from a set of m items, we want to predict a rating from 1 to 5, for example. And collaborative filtering is actually a data-driven approach for this specific problem. And it predicts the user preferences for a product using the user preferences for other products and preferences of other users. And it usually can be improved by adding side information such as characteristics of users and products. One way to think of collaborative filtering is as a matrix completion problem, where we consider all possible ratings as a big matrix, and we observe only few elements of this matrix, which has rows for all items and columns for all users. And the goal here is to fill in the missing values. And as I said, this matrix is actually usually very sparse. For example, in Netflix challenge, we have 8 billion possible ratings, and we only observe 100 million of those ratings. So the matrix factorization approach for this is to approximate the ratings matrix as a product of two lower rank matrices. The first one represents the item factors, and the second one represents user factors. Now, each element in this original matrix is approximated by a dot product from a row from the first matrix and a column of the second matrix. So more specifically, the estimated rating can be written as I said, as a dot product between item factors and user factors. And we usually add user-specific bias, item-specific bias, and a global bias. So this makes the total parameters for the model is the global bias, and biases for all users, biases for all items, and factors for all users, and factors for all items. Usually these parameters are estimated given some training set of observed ratings by minimizing the mean squared error. That is the average over the squared difference between the estimated rating and the original rating over the training set. Now, this formulation usually suffers from severe overfitting, and this leads to poor generalization on unseen user item pairs or held out dataset. And this is especially serious as we deal with very large number of users and products. And this is true because users usually consume or watch only a small fraction of the available products. Now, the typical way of dealing with overfitting is to add a regularization term. And the standard regularization term used in matrix factorization is LT, norm penalty, which penalizes the norm of the parameters. In this work, we are more interested in another form of regularization, where we simultaneously estimate our parameters to perform well on another related task. This framework is known as multitask learning, where usually we have several related tasks, and instead of training a specific model for each separate task, we train one large model for all tasks, and then we this forces the parameters of the model to explain several related tasks. Now, how this helps in regularization is, if we look at from the point of view of the first task, all other tasks act as regularization. Now, what could be a related task for recommendation? And we know that typically the ratings are accompanied with reviews. For example, a user who gave 5 stars for a movie called Free Willy also wrote, "This is a great adventure movie that children and adults alike would love." So we would consider that modeling natural language reviews is a related task. And this is specifically true is because users often write reviews that justify their ratings, and they describe features about the products that affected their opinions. So in this work, what we can do is that we can regularize the parameters of matrix factorization such a way that instead of just using the item factors and user factors to predict ratings, we can also use them to model text reviews. This is especially helpful because text reviews have much richer content than ratings. In this work, we actually proposed 2 different neural network-based models for modeling reviews, and we use those for regularizing matrix factorization parameters. Previous work used latent Dirichlet allocation for modeling reviews, and we compare our work with them, and we provide some explanation how our models compare with them experimentally, and give some insights how they differ actually in how they model the reviews. So when we talk about review modeling, we assume that we have a set of observed reviews, a review given by a specific user for a specific item, and each review is considered as a sequence of words. Now, when we say modeling reviews, we actually mean modeling the conditional probability of each review giving some corresponding product. So given that we know that we are talking about some product, what is the probability of observing some sequence of words? So, and this is typically also parameterized with some additional parameters that are specific to the review model. Now, we typically estimate the parameters of the review model by minimizing the negative log likelihood. That is the average over the log probability of the sequence, negative log probability of the sequence, conditioned on the item factors and parameterized by the model parameters. Now, in this work, since we have a joint model, which is both trying to estimate the ratings and the reviews, we optimize our whole model as by minimizing the convex combinations of the two costs. The first one is the mean squared error that we just explained, and the negative log likelihood. And we notice that the two models share the item factor parameters. So now the first model that we present here is actually based on distributed bag of words. Here we assume that the review is just a bag of words. So we mean here is that we ignore the order between words, and this makes the probability of the full sequence factorized to be the product of probability of individual words. Now, how do we implement that? What we do here is that we take the item factors and we apply an affine transformation using learned parameters, W matrix and bias. Then we apply a softmax, and then we get a distribution over all possible words in the vocabulary. We call the joint model of matrix factorization and the distributed bag of words BOW-LF model. The second model is actually based on recurrent neural networks. And so here we model the full sequence. We have any independence assumption across words. So we use the chain rule to factorize the joint probability of words, which turns out to be the probability of the first word, and then the product of the second word given the first word, and the third word given the first and second, and so on and so forth until we get the full sequence. This is typically called the language model. And recurrent neural network can model this distribution using what it defines as a hidden state. So in each time step, a recurrent network defines a hidden state, and this hidden state is defined recursively as a nonlinear function of the previous time step hidden state and the current time step word in the time step. And also at each time step, we make it consider the item factors. Now, once we get the hidden state for all time steps, we can predict the probability of a word of a specific time step as a function of this hidden state. More schematically, we take the item factors, we predict the hidden state of the time step 0, and based on that, we predict the first word. Then, given the first word, what we do is that we compute the hidden state of time step 1 based on the hidden state of the time step 0 and the current word, and then we produce the probability of the next word, and so on and so forth. This gives us the matrix factorization model plus the RNN language model. We call it the LM-LF model. Now, for our experiments, we evaluate our approaches on Amazon Reviews dataset. This dataset has over 35 million ratings and reviews from over 6.6 million users and 2.4 million products. The dataset is divided into 28 subsets, and those subsets are based on product categories such as music or books. We compare our approaches with standard matrix factorization with weight decay. So we would like to compare how does considering the review compare with just normal weight decay. We also compare with the HFT model, which uses LDA as a review model. So here I present the results on all 28 dataset. We see here that first of all, I'm sorting here the data sets according to their sizes. So we have the smallest data set has 27,000 ratings, and then the biggest one has 12.8 million ratings and reviews. So here we have 4 approaches: the matrix factorization, HFT, BOW-LF, distributed bag of words, and recurrent network-based model, LM-LF. We report here the mean squared error, so the lower is the better, and we put in bold the the result that is best across the different approaches. We see here that the BOLF model actually dominates all other approaches on almost all of the data sets. One observation is that we actually observed that in general, all models that use reviews perform usually better than matrix factorization. We also observed that both the recurrent network or the neural network-based models outperform typically the HFT model, especially as we increase the size of the data set. And finally, we observed that the BOLF actually even gets better results than the recurrent network-based model. So just to summarize the results, BOLF outperforms all models on 27 out of 28 product categories. Both BOLF and LMLF generally outperform other models, especially as the size of the dataset increases. And one of the surprising finding of this experiment is that BOLF actually outperforms the LMLF, which was surprising for us because we were expecting a richer language model to give us a richer representation, product representation, which helps in rating prediction. But it turns out that this is not necessarily true. And we hypothesized that this is possibly because the way it encodes information in this product representation might not be very useful for the rating prediction procedure. More specifically, the recurrent neural network encodes information in a highly nonlinear way, and matrix factorization uses this representation in a linear manner. But we would like also here to understand why would BOLF actually outperform HFT. So BOLF uses distributed bag of words, and HFT uses LDA, which is sort of bag of words model. Now, HFT is based on LDA, and LDA is a standard topic model, which represents reviews or documents as a mixture of topics. So specifically, what it does is that for each review, it samples what we call topic proportion from a Dirichlet distribution. This is a stochastic vector. And now, for each word in the review, we sample a specific topic from this stochastic vector, or from a multinomial distribution parameterized using this stochastic vector. And then we sample the word based on this topic and some parameters W star. Now, what HFT does is that it replaces the sampling from a Dirichlet distribution by using the item factors, and it applies a softmax function. Now we have another kind of stochastic vector, but that depends directly on the item factors. And the rest is the same as any LDA model. Now, to compare how BOLF differs from HFT, we looked in more detail into the probability of a word conditioned on a specific item factor. So in BOLF, the probability of a word is actually a softmax function of the product of item factors with some weight matrices plus a bias. In HFT, however, the probability of a word is actually the sum of or the weighted average of probability of words given specific topic. This is, as we said, the probability of topics, or we call it the topic distribution, the topic proportion, is actually a softmax of the item factors, and this is multiplied with some weight matrices, a weight matrix W star, which is constrained to have columns as stochastic vectors as well. And this is typically done by applying a softmax on each column individually. So if we compare these two equations, we see that the BOLF actually does the product and then applies normalization, while the HFT applies normalization on each of the product components and then does the product. Now, this means that we are adding more restrictions to the item factors and also the parameters that we are learning. Another way of saying this from a perspective of neural networks is we we can see that the BOLF is actually what we call in the literature a product of experts. We mean by expert here is a distribution over of vocabulary words. So it's a product of experts because we have a mixture in the log domain. While the HFT is a normal mixture of experts, where each column of this matrix is actually an expert. It's a distribution over vocabulary words. Now, we know from Hinton's work in 1999 that product of experts usually model easily the peaky distributions in high dimensional spaces. We mean here, the peaky distributions here is the distribution of words in the vocabulary. And probably this what helps the product representation to be better in BOLF. So to summarize the outcomes of this talk, we developed two new models, BOLF and LMLF. The first is based on distributed backward representation, and the second is based on recurrent neural network for review models. And we use those to regularize matrix factorization. We also show that the BOLF model achieves state-of-the-art result on 27 out of 28 Amazon Reviews datasets. And both BOLF and LMLF outperform HFT, especially as the data size increases. And finally, we show that in general, or actually the weighted average of improvement of the BOLF over the standard matrix factorization is about 20%, while its weighted average improvement over the HFT is 5.6%. Thank you.
Any questions?
Thanks for your talk. So, because here in your work, the review is represented as a bag of words, so have you considered the sentiment the user expressed in the review, the sentiment? Maybe through the sentiment analysis, you can know whether the reviewer, the user is positive or negative about the item, and even you can get the user's sentiment over some attributes or features of the product.
So this means that we are adding extra information that might not be available. Usually for example, in Amazon, you give a rating for a product and you just write a review. You don't really give extra data which tells if this review, I mean, you can ask the user to give extra information, but that adds more burden on data collection.
I mean, the sentiment is contained in the review. For example,
it is
I like this, maybe I write some review to the hotel and I will mention the hotel's food service. So this information are contained in the review.
So this actually contained in the review model.
Yeah.
Once you model the distribution of the words or distribution of the full sequence, you've captured. Usually, we can use those models to predict sentiment. That's standard way of also using language models. So it is contained in the model. So a good language model would model the sentiment. That's why I'm going to argue. So I don't see what you're trying actually to get to like.
Because we also done some similar work and we consider the users, for example, the opinions, the contextual opinions in the reviews. So this is explicitly modeled in our algorithm, and we find that it can help improve the accuracy.
So the goal here is actually rating prediction. So you have the rating, the actual rating of a product,
yes,
and the review is extra information about how you feel about the product. I don't really see how when you add sentiment about the review itself, it's not our goal here. That's how I see it.
Oh, okay. So maybe we can discuss.
Sure.
That. Okay.
Thank you for your talk. As I understand, you use just regularization on item vectors with
I cannot.
reviews.
Sorry, I can't hear you. Sorry, can you just raise your voice?
are you using these ratings as regularization on item vectors, not just user vectors? Yeah?
Yes, here we are using the reviews to regularize only item vectors.
And don't you don't use any regularization on users, yeah?
No.
And what do you think if you will add user vectors in review model? It will lead to overfitting or not? What do you think?
So once you regularize more, you have probably less overfitting, but that's what you expect in general. But what we actually observed, I actually tried that. Actually, that was my main motivation of conditioning on both user and item. But I observed that it's unfortunately like worse. I have some hypothesis why but typically I just reported the best results from several experiments that I did.
Okay, thanks.
So I don't quite follow in the intuition that the review will help regularize the item vector, because usually the reviews are probably very highly correlated with ratings, right? If you have a high rating for something, you probably write very good reviews about that. And in general, regularization kind of prevents, say, the item vector goes too big or something like that. Can you elaborate a little bit more how you think this will help with regularization?
Well, if they don't correlate, then that's not a related task. I mean, you should have some related task, which gives you extra information why specifically the user. Once you have more information why the user liked the item, you can probably generalize to other cases which share those factors with it, but don't specifically ascribe to it. Like different products can have similar, or like very close product can have similar reviews. That's why you would generalize easily. You would deal more with data sparsity with this. Like one single review can be much more informative about this product than just a single number, which is 5 or from 1 to 5. That's kind of the argument here.
Yeah, but that reinforce the ratings rather than say regularize or.
Well, it gives you more information. Why is this rating make sense? And once you get this information, you can generalize to new cases. When you don't know what's the rating, you just want to figure out. Because it's just similar to the other product, then you would be able to tell.
Thanks.
So it's here. My question is about the validity of your evaluation. So I think that you should really take the baseline to be an ensemble model that takes, for example, LDA and matrix factorization. So basically, you have this multitask training, and you call the text reviews as a regularization component, but you really train on both pieces of information. So why do you compare only against LDA or only against matrix factorization when your method uses both as?
Probably I didn't make this clear, but the second model uses both matrix factorization and LDA. Because LDA is not used to predict the ratings, it's only used to model the reviews. And then the matrix factorization in this model is what really is doing so the first matrix factorization is predicting ratings, and so regularized using L2 penalty. And the second model uses matrix factorization for predicting rating, but also uses LDA as a review model. And our models use matrix factorization, so we all have the same matrix rating prediction model, but we differ in how we regularize those models. And I say regularization here because in test time we don't observe the review. We just observe this user and this item and give me the number.
Okay, further questions? I have one quick one. So you say your model is better in some domains, but in many domains, but not in all.
In better than what?
Pardon me?
Which models?
Your approach is better than previous ones in most of the cases. Did you look at those cases where you were not better? Any explanations why in some areas it didn't work better?
So to be honest, I once you get like extensively like better results and most of the data set, I mean, I don't really have good explanation why in this specific case it was worse. I mean, data always has noise and it has our own specific, I mean, you can always make conclusions about like large amount of experiments, but a large amount of results, but explaining specific results is just pretty hard. So I don't really have specific explanation for this specific case. I have some intuitions why would this model work better, which I presented, yeah.
Okay, yeah, there's one more.
Thanks for your presentation. You said you use part of speech tagging for all the reviews, right?
No.
No?
It's basically just the words. We don't know any kind of pre-processing on the text.
Okay, and well, I've seen Macaulay's model. It's pretty fast. How do you compare to his model in terms of time processing? Because 35 million reviews, it's quite a large data set.
I'm sorry, I don't understand your question.
Well, how does your model compare in time? How long does it take you to train the model?
Oh, okay, yeah. So one of the advantages of using distributed bag of words is much faster to train than recurrent networks. That's typically that's known for sure. So I did not make. It depends. I mean, comparing with other approaches is a bit tricky because you have to set up the exact same setup and what I would say is that bag of words, distributed bag of words, is very easy to train. It's very quick to train. HFT is actually very quick. The code was provided by the authors. It was very quick to train. But the recurrent networks was kind of challenging. That's one of the drawbacks of this model, as usually known. And we usually need a GPU to train it. And even with GPU, the largest model would take several days actually to converge. Yes, for the largest data set. For the small data sets, it's not that bad.
Okay, if there are no further questions, thanks, speaker.
Thank you.